Okay, our first speaker is Jeremy Crane. From NASA Ames. Jeremy's done lots of great work in planning and scheduling for space, including for the human exploration program. And he's going to be talking about scheduling ocean color observations for geostationary satellites.
Right, so, is that on?
I think you're not a song speaker, so we should be fine.
Yeah, that's kind of what I thought.
The recording, though, you want to.
Oh, yeah. I can't hear it.
I think you open it up. There's a button on the inside after you open that.
After you open it up. Here we go. He's absolutely right. When I press it on, it doesn't seem to. There we go.
There we go. How about that?
There you go.
All right, very good.
I'll give you a hand so you know some kind of 18 plus 1? Yeah.
Something like that. Okay, in order to catch up a little bit, I'll skip over the outline. So the work that we did here is focused on an earth science mission that's in the planning phases to do what's called ocean color science. So the idea is to use visual spectrum instruments to survey, in this case, the oceans off the coast of the United States in order to do science based on the color of the water. So what classes of science are we talking about here? One class of science has to do with, well, that was probably a bad idea. There we go. Where's my pointer? Here we are. So I think we heard in one of the workshops about harmful algal blooms. So there are a variety of these. They're quite dangerous. They're not terribly well understood. You can actually survey some of these organisms from space. Carina brevis is responsible for red tides, not only on the coast of the United States, but elsewhere. It turns out there are some other algal blooms that occur in freshwater. In particular, this Microcystis aeruginosa algae produces a variety of water-based and sometimes aerosolized toxins in the Great Lakes. This image is from Lake Erie in 2011. You don't want to go swimming in that. But you can also do a variety of other things. You can produce biological models of the production of plankton as a function of both coastal zone and ocean temperature. And you can also do things like survey erosion as a result of rainfall, deforestation, and so on and so forth. So these are the application areas. And in particular, NASA is investigating not just satellites, but geostationary satellites with instruments that are sensitive enough to do this class of work. But the mission that's in formulation, which is called Geo Cape, at the moment they have an interesting problem, which is not only how do you actually schedule the observations once the instrument has been deployed on the satellite, but in this case, multiple instrument designs are being considered, and they have some interesting differences. And the science community doesn't really have a good handle on which instrument is preferred. And so the work that we're doing here is not only to build a scheduler in order to solve the resulting problem, but also to use that scheduler to help select which of these two instrument designs is the right one. So that is what we're going to talk about. So without belaboring some of the complexities of the instrument design, there are two features of the instruments that are important to us. The first one is how much of the surface is observed when the satellite is pointed at a particular place. And you'll notice in particular, I have this notation at nadir. So as it turns out, when these satellites are pointing off nadir, the scenes are distorted. We'll see some pictures of that in a minute. But for the most part, what we're interested in here is this first instrument has this great big 512-kilometer square scene that it observes. And the second thing that we care about is how long does it take to acquire the scene. In particular, slew time to redirect the instrument is very, very small in these cases. Time to acquire the scenes is very large, comparatively speaking, so that's the thing that sort of dominates. So the first of the two instrument designs is shown here. It's called the filter radiometer. Don't ask me what a filter radiometer actually is, because I don't know. For all purposes, we only care about the area and the scan time. The second instrument is rather more complicated, and in order to simplify, what we look at instead is the fact that the scene that's observed at nadir is, instead of a big square box, it's this kind of long and skinny box. And you'll notice that the scan time is rather slower. So, big scene, fast scan time, long skinny scene, slow scan time. You would imagine that the instrument on the top is preferred. Turns out it is, but we'll get into why later. So, when you actually look at how the scenes are laid out given these different instruments, the first thing you notice, as we said, here's a scene over the Gulf of Mexico, and it's almost a perfect square. But these scenes that are up at the northern latitudes, and especially the northwest and the northeast, they're distorted. They cover more area. In particular, they cover more of the water. It turns out that spatial resolution is reduced, but we didn't care about that, and that wasn't a big problem. The real important message here is that we only require 19 scenes for this filter radiometer instrument to cover the US coastal waters. By contrast, when you go to the other instrument, whose nickname is Cody, you can see now you have this long skinny box, and you see how it kind of bends to the left and bends to the right. But we need a lot more of these scenes in order to cover the same US coastal water zones, and in particular, we need about twice as many. So 19 scenes versus 38. The Earth is a cloudy planet. This is a really beautiful but very evocative image. All this white area here, this is the average global cloud cover for 2009. So you can see there are these zones where it's very, very cloudy almost all year. What are the implications of this for this scheduling problem? Both of these instruments are visual spectrum instruments. What this means is that if it's too cloudy, we can't take a picture. But too cloudy is conditioned on what part of the US coast you're actually looking at. So when we go to the filter radiometer instrument, for instance, what we have is cloudiness thresholds that were given to us by our science community that tell us when it's too cloudy to take a picture. So in the Pacific Northwest, which I grew up in, if you have less than 75% expected cloud cover over a scene at a particular time, science community says, well, we can live with that. Go ahead and take the picture. If it's more than 75% cloud cover, don't take the picture. By contrast, over Southern California, where it's sunny all the time, if it's more than 25% cloud cover, then they're like, nah, don't take the picture. And as you can see, there are these variations throughout the US coast, including the Great Lakes, that apply and tell us when it's all right to take a picture. Okay? Cloud cover varies quite a bit day by day. Shouldn't be a big surprise to you. But just to give you a sense of what this actually means, if we take a pair of scenes and take a look at how the cloud cover varies throughout the day and compare that hourly or by the minute variation throughout the year, we can see some very, very interesting things. So this is the number of scenes that pass the cloudiness threshold for that Cody instrument, the one with the long skinny boxes, on January 1st of 2015. Now, some of these variations arise because we also take into account when the sun rises and the sun sets, but throughout the middle of the day, every scene is in full sun. And as you can see, there are these variations throughout the day. And cloudiness and geographical variation play into this a little bit. But what's very interesting is that no more than 12 or 13 of the 38 scenes can actually be imaged on January the 1st. By contrast, on April the 1st, we're up to almost 25, 26, 27 scenes. So from a scheduling point of view, what is this really telling us? It's telling us that clouds are dramatically reducing contention for the instrument. And this is what we tried to explain to the science community. You can't just look at these sort of gross measures of how fast you take a picture. You need to take this class of information into account to figure out whether a particular instrument design is or is not going to be viable. So that's why we contended we had to build a scheduler in order to help them choose the instrument. Okay? So the last piece of the puzzle is what the scientists actually wanted out of these schedules. They weren't interested in just a raw, how many times do you image each place count. They wanted sort of relentless observation. And so what this matrix here is doing is it's capturing their sort of intuitive science requirements. So they had sort of a survey mode, and then they had a targeted science mode for exciting events and disasters like oil spills. But what you see here is that they said, well, we'll live with 2 hours separation, but if you can observe your scenes every hour, that's what we really want. And similarly, in the targeted science mode, we'd live with an hour, but we really want every half hour. And so You can't just build a scheduler that says, I'm just going to maximize the count. What you actually have to do is record how long it is between each successive observation and get quality out of that. So the trouble is, they didn't really tell us, from a science point of view, what happens if you observe a scene and there's 45 minutes temporal separation. So we made an assumption, which is what we always do, and we built this linear scoring function that degrades linearly from the minimum separation to the maximum separation. But the other thing we needed to do was choose the actual scoring values. And this is where things got a little bit more tricky, but basically they asked us, make sure that the scheduler does the minimum first. In other words, make sure that you can achieve that 2-hour separation in survey mode before you even try and satisfy the more tight requirement of an hour. And so that's why we chose this value of 0.9 and 0.5. So if you get 3 observations with an hour separation between them, that gives you a grand total score of 1, which is just a smidge better than 2 observations separated by 2 hours, and that's sort of what they wanted. So now we have a nice scoring function. We can take any schedule. We can return to you a sound value of schedule quality, and we're almost ready to actually construct something that a machine can solve. So the way we set the problem up, it's pretty straightforward. We know exactly how long we have to scan each scene. So once we compute the sunrise and sunset times for each of our scenes, we discretize time. We can then take the cloudiness data that we have. We can apply the cloudiness thresholds and block out any scenes that don't satisfy the cloudiness threshold. This gives us the legal set of times when each scene can be observed. We can then say, all right, well, if I'm in a good world, best of all possible worlds, I might be able to achieve the minimum separation for one scene. But having done that, I may not be able to observe another scene because the instrument can only take one picture at a time. And so I might have to suboptimally schedule a second scene by having a longer than desired observation interval. And so that's the sort of intuitive setup. The paper and some backup slides have the formalisms that we use, which I probably won't go into. But hopefully you get the idea. So how do we actually solve the problem? Well, it's a scheduling problem, not a planning problem. We don't really need automated planning technology. So we first looked at linear programming, mixed integer linear programming, and also constraint programming. And we wanted to compare both of these, even though there's some pros and cons to them. So mixed integer linear programming is really, really good for solving optimization problems. They're very, very strong commercial solvers available. We were very lucky we had Cplex at our disposal. But it's kind of hard to build the models. And in particular, getting that temporal separation into the scoring function was the tricky part. And Tony Tran, our intern from Toronto, built that model for us. And that was really awesome. Very, very clever. Constraint programming, by contrast, very, very strong propagation algorithms, not quite so good at optimization, lots of specialized constraints that one can make use of. So a really good and interesting comparison to do. So in order to build some test suites, we worked with some folks at Langley Research Center who maintain databases of data from the GOES satellites, which do, they're geostationary satellites that do weather observations. The GOES satellites that are up right now provide a half-hour downlink of cloudiness data all over the world at about 4 kilometers resolution. So what we did was pretended that that was our cloudiness prediction, which is actually not a very bad thing to do. We took those clouds. We assumed that that's what we had at our disposal. We then used that, applied the cloudiness thresholds in order to construct our daily observation scheduling problems. And we did that for the first of the month, for every day of 2015 except for every month of 2015 except for December. The second thing that we did was we looked at the science goals consideration, and it turns out the science community wasn't quite prepared to say this is how often you would have targeted science mixed with that survey science. And so we built a stressing case problem set where all the science is targeted science. So remember what that means is that ideally those scenes would be observed every half hour, but you're willing to live with an hour. So if you like, you sort of have twice as much work that you have to do. And then the second problem is the sort of more common survey problem where everything can be observed every 2 hours, but ideally you'd like an hour. So that gives us a grand total of 44 test instances. And again, just to emphasize, the science community doesn't expect that you would ever have all targeted science all day long every day, but it's a great stressing case. And it's really going to ring out both the instrument designs on the one hand and the schedulers on the other. Okay? Anybody still awake? Good. At least one person is still awake. Okay. So, first question. Which of the two solvers works best to help us do the instrument analysis? So the short version of the story is that MILP dominates constraint programming, although the story is not quite as obvious as it might seem. So I'm going to spend a little time walking through the legend here because it's a little bit complex. Pale blue is the survey problem instance, filter radiometer instrument, mixed integer linear programming solver. Dark blue is survey science problem instance, filter radiometer instrument, constraint programming solver. Similarly for the rust colors. So the score is basically the schedule quality using that linear function that I described that was achieved by the schedulers. It doesn't have a particular intuitive meaning, so don't get too hung up on that. But as you can see, basically, for the most part, the mixed integer linear programming solver is doing a little bit better than the CP solver. In the wintertime, the difference is not so profound. In the spring and summer, the difference is much more profound on those survey problems. And you see the same pattern, although the differences are quite a bit larger on those targeted science problems where you have twice as much work to do. So, MILP solver good, CP solver bad. That's for the filter radiometer instrument. The legend is essentially the same when we look at the Cody problem instances. There is an interesting notable failure. The mixed integer linear programming solver kind of dies horribly on some of these problems in September and October. We're not totally sure why, but that was sort of interesting. But other than that, the pattern is the same. Mixed integer linear programmer solver better, CP solver bad. So we throw the CP solver results away, and now we ask ourselves which instrument design is returning the better schedules. Are we getting better schedule quality out of the filter radiometer instrument or the Cody instrument? We have a little problem. The problem is there are twice as many Cody scenes, and the scoring function doesn't take this into account. But because there are exactly twice as many scenes, we said it's roughly acceptable for us to simply scale the Cody results, or by the same token, scale the filter radiometer results, multiply by 2, divide by 2. Now we have an apples-to-apples score comparison, and we can do a heads-up comparison of the results of the schedulers in order to decide which instrument is better. When we do that, here is what we find. So again, this is basically that schedule quality function, except now it's scaled for Cody. Basically, we divide by 2 in order to get our comparison. And what we see is that filter radiometer, which is blue, is doing a little bit better than Cody, which is dark blue. And again, the differences become a little bit more profound in the summertime when you have less contention for the instrument. And on the targeted science problems, the differences are very large. So why is this happening? Why is it that you get such a dramatic difference in score increase when you have the targeted science problems? Well, essentially what's going on is that when contention for the instrument is relatively low, the schedules are relatively inefficient. There's a lot of slack, and there's a lot more room to make up when you go to that targeted science problem and you have twice as much work to do. But in the summertime, the efficiencies are already very high. You're sort of squeezing in everything you can because there's less contention for the instrument. And so in this case, Cody basically is already doomed, and you just can't squeeze anything else in. So that's what's going on. All right. A couple of points about what we experienced. I initially expected that these problems weren't going to be all that hard. They turned out to be quite hard. CPLEX was not able to optimally schedule these problems given an hour CPU time on a reasonable desktop machine. So these problems are hard. The other thing is that we conclude pretty straightforward way that our MILP coding is better. It probably could be improved. CP is suffering because it's trying to do all this constraint reasoning, and you really don't need that power. You need to optimize. CP is not very well suited for that. There's plenty more work to do. There are a huge number of very interesting heuristics that we could try. The science community has a lot more work to do in order to refine what the science problem is. We never experimented on problems with mixtures of survey and targeted science, and the list goes on. So I'll take questions. Thanks. Yeah, so the question is, are those scene definitions fixed? And the answer is yes. They don't get dynamically selected throughout the day or throughout even the month or year.
And is the satellite stationary, or does it move around with the Earth? Do you have to set it as well?
So it's geostationary, which means it's about 30,000 kilometers from the Earth, and it's essentially capable of staring at exactly the same place all the time.
Would it be a single machine, disjunctive scheduling?
Single machine, disjunctive scheduling with this temporal preferences, yes.
Can you see how many jobs roughly you expect?
Well, so you saw it here. It's all dependent on that scan time. So the filter radiometer instrument scan time is something on the order of, what, a minute and a half. But if you have 16 hours of daylight, that's a few hundred tasks, right? So it's like a few hundred time slots that you have to fill. That's why the problems are so big.
And it triggers to get the distances from one job to the next.
That's right.
So have the scientists accepted your justification for what machine they should be building?
There are pieces of information that CODI instrument returns that the filter radiometer instrument doesn't return. That's why they'd really prefer to use it. Quite honestly, I don't understand what the actual differences are, but you know, you can think of it sort of as amount of spectra, visual spectra that's returned. It's the returns on those spectra from the water that basically lets you do these science. So they're off doing basically a ground calibration and validation instrument campaign in the oceans this year, so I'm not sure what instrument they're going to get. But yeah, they like the analysis.
Next up, we have Steve Jin. We talked about planning and control of marine floats in the presence of dynamic incidents.
Okay, so I'm going to be talking about some work that Martina Trosch and myself did at JPL in collaboration with Yi Chao and John Farrar of Remote Sensing Solutions. And this is work in trying to work in autonomous underwater vehicles. And there's a specific kind of vehicle that we're working with. So to first start out with, why does NASA care about the oceans? Well, I didn't know I was going to go after Jeremy, so he covered all of this already. Basically, from space, you can observe the surface of the ocean. Of course, a lot of the interesting stuff in the ocean happens deep underneath. And so we need to send in situ assets in there. And then I'll talk about a particularly interesting use case at the end where we care about this. So we want to get down here. And you have to sample this with single individual assets. So it can only each sample one point in space and time. Whereas this remote sensing, you take these huge swath images, sometimes as many as thousands of kilometers by thousands of kilometers. There's all kinds of different assets. If you get into this, they're floaters, which are just literally these things you throw out into the water and get data on the surface wherever they are. Vertically profiling floats, which is what I'm going to be talking about today. It's a float that only has vertical control. It has a buoyancy instrument in it. These can dive quite deep. They're not that expensive, tens of thousands of dollars, and the cost is coming down every year. Then, of course, there are sea gliders and AUVs that are more ability to control, but they're more expensive. And also, they're more risky. The operators of these are more risk averse. When I started working in this area, I thought, oh, finally, we'll get to go and risk these things out there because they're not like a $200 million spacecraft. Shockingly, when you're talking to a scientist about his $4 million AUV, he doesn't want to risk it. So this particular problem that we're looking at is called a virtual mooring. So what they do is they take these different kinds of instruments and they moor them to the ground, to the ocean bottom at a particular location. And what that means is they get all the data at that particular point at every timestamp. And they're even, sometimes they take multiple instruments and put them on the same chain so they get multiple depths, or they, in fact, have vertically profiling instruments that can go up and down a chain. And this is very expensive. It costs about $1 million to moor one of these devices, and that's not even counting the cost of the instruments. And once you moor it there, you can't, like, move it around. So the concept of a virtual mooring has been proposed by multiple people. The idea is you have an autonomous vehicle, and it tries to station keep. Interestingly enough, Sometimes you don't actually want the station keep. So one of the most famous moorings in the world is what's called M1. It's run by MBARI, the Monterey Bay Aquarium Research Institute. And they have actually these S2 and S3 that are further out. Sometimes there's a particular feature that you want to sample across. So this is showing a linear front here, actually as we get later on in the time. And the scientists want to sample across that feature. Once you have this ability to try and control your position, you can actually look for profiles in transects that are not static. Okay? These particular vertically profiling floats have been used a lot. The most famous is what's called APEX. About 6,000 of these have been built. And most of them have been used in what's called Argo. Argo is run by Scripps, and they've deployed gazillions of these floats all around the world. Okay? However, they do not do any smart control. Basically, they rely on the fact that the currents are very slow deep down, and so they stay deep down so they can roughly station keep, and then once every 10 days they shoot to the surface and back again. And the reason why they do that is this vertical profiling information is in fact what you want. And so they're getting one profile effectively every 10 days. And then you can do the math. The lifetime is 150 profiles because it's battery powered. So each one of these is going to last about 4 years. We actually did some experiments in actively driving these with a current model called HICOM. That was actually published in IROS a few years ago. This map is a little misleading. If we go to some places like the Sea of Japan, there's actually concentrators. In other words, this is where the floats go to die. So they all go there and they get stuck there. They can never get out because of the way the currents are. So you actually want these all evenly distributed, and it's not an easy problem. You can think of this as when people go hot air ballooning with Montgolfiers, right? They know something about the winds, and they can control the vertical position, and they're trying to get places. So we actually work with a particular kind of float called EM apexes. These are apexes that are relying on this very unique electromagnetic instrument, which is a collar that relies on the fact that the floats spin as they profile, and it can actually measure the float velocity in real time. So this is actually a huge breakthrough in ocean science, and we'll see why we're interested in this later on. These were developed actually at the University of Washington. These are our collaborators, James Girton and John Dunlap. The key things here are the vertical velocity. Here is about 0.12 meters per second. Or it's much easier to think about it. An up and down, a yo-yo as we call it, of about 500 meters is about 3 hours. And then when you're at the surface, you upload your data with sat phone. You could actually wait until you recover the buoy, but people actually want this data relatively quickly. The other advantage of uploading it with sat phone is if you lose the buoy, you didn't lose all your data. We actually model this as a sawtooth. In reality, if you think about it, since at the top it floods something and it has a negative buoyancy, it's going to be more like a sinusoid. Okay? We actually use, the unique thing that we do is we use a particular ocean model to try and predict where the float's going to go. The one we use is called ROMS, Regional Ocean Modeling Simulation. The particular model we use is the US West Coast Pacific model. It's a 3 kilometer by 3 kilometer XY resolution. For some reason, the oceanographers call this zonal and meridional. Don't ask me why. It has variable depth, so you can see all these different depths. And then they nest these models. So there's a 3 kilometer model that runs all up and down the west coast, but in some areas of interest, like where we're going to be deploying, we have a 300 meter model. It models things like salinity, pressure, and ocean currents. All we care about are the ocean currents, the ocean velocities. And so we're specifically trying to look at things like particular events. Some of the details of the model. There's a 1-day advanced forecast of 3 days. What does that mean? Every day at 3 a.m., they forecast from 6 a.m. out for 3 days. The forecast predictions are at 1 hour temporal resolution, and the model is updated at 6 hours. But really, the model changes a lot from day to day, but not every 6 hours. The reason is the satellite data input, which is the primary input to this model, is only daily. Okay, so the 6-hour update is not going to provide a lot of new data. So for our experiments in simulation, we have experiments both in simulation and in the actual deployment. We construct this common thing where we have a planning and nature model. We take our best prediction at any point in time, and we call it the nature model. That's going to be our real data. then we take that and we decimate it in some way. In this particular way, we took out probably the most important information. This is the high-frequency radar current data. From the shore, you can look out about 150 kilometers and see the ocean currents using a particular kind of radar. And obviously, currents are very important. We also forced that ROMS version for the planning model to forecast with 10-day-old data. Okay, so it's forecasting 10 to 13 days out. Okay? So the question, the hypothesis that we have is the following. Can we use this predictive ocean current model to actually realize a virtual mooring? And what are the problems that we think would stop us? One is the model's not very good. Okay, so we have some sensitivity experiments there. The second is, even if the model is good, if everywhere at all depths the current is just driving you west, you're screwed, right? In reality, we don't have to do this perfectly. We just have to beat the current state of the practice. We were quite shocked to learn that the current state of the practice is the following. Don't use any model. Don't use any model for adaptive control. Second of all, they don't actually use this when they develop the deployment location. So one of the things that Jeremy was talking about, which is a very powerful idea in planning and scheduling, is use your planning and scheduling not in operations but in design. So we actually want to select the deployment locations because we believe that we will be able to maintain them. That's at least one criteria. Okay? So this is a hybrid planning problem because the following. The float control problem is actually a continuous problem. In theory, we can actually, at any point in time, say that's the depth we want to go to. The only thing that's stopping us from that is, first of all, it's a little bit more complex control software for University of Washington, and they don't really like that. And second of all, you actually control the buoyancy, not the depth. And that's a calibration problem, because in fact, one of the things you're measuring is the differences in pressure. And so those are weather influenced. Okay? We specifically discretize the search space for this particular deployment, this particular experiment, in the following way. Just when we're at the surface and just when we're at the bottom, we pick a discrete depth that we're going to dive to. And then when we're at the bottom of our profile, we can wait an arbitrary period of time. Okay? So that's very restrictive. We basically do that to restrict the search space, but maybe later on we'll beat that to death and do more. The second thing is the ocean is continuous in its quantities, or near continuous, but in fact our model is not. It's a gridded model. So we started out with actually just searching in this simulation or model space completely completely discrete. In other words, at the 3-kilometer boundary, it'll like have a sawtooth. Then, we realized that was always bad, so then now we interpolate in X, Y, and T. Turns out it doesn't actually matter for all of our performance, both in deployment and in simulation. And the reason we believe this is twofold. First of all, we're looking at integrated currents over a profile. So the smoothing of it just pretty much evens out. Second of all, the performance is dominated by the model accuracy, as we'll see. So this is an example of how the model is or is not good. And it's really a question of, are you a glass half full or glass half empty kind of person? So this shows actually the planning in nature models for the zonal currents and the meridional currents. This is actually showing off the coast of Monterey, this is an east-west daily variation. So these are basically tides. Okay? And you can see these numbers are all over the place. And then these are a little better. If you look at the RMS error, and this is the number of advanced days prediction, this is the correlation coefficient with advanced days prediction, 2, 4, 6, 8, and 10 days. You can see the correlation coefficient here is actually effectively 1 for 2 days, and then they have what's called decorrelation here as you get further on. And it's worse in the east-west dimension. Okay? We also study the RMS error, but for some reason I do not have that graph here. Okay? I apologize. Okay, so what do we do with all of this? We basically use A-star search. We started out with a 0 estimated completion cost. And we search in the planning space, and then we evaluate in the nature space. We have the following objective function. This objective function has 2 weights. This is the time penalty. That's the amount of time since you were at a particular depth. Okay? So that's what's to keep you from just staying at the bottom the whole time. If you really want to maintain your presence, your position, you just stay at the bottom. There are almost no currents. You're fine. This distance penalty, sorry, is the actual distance that you are from the target point at that time that you took that last depth data point. Okay? So this is what penalizes you when you get blown way off from your target point. Note that if you wanted a moving profile, you just measure the distance from your moving profile that you want to do, if you want to do transects back and forth. And in fact, that's what we do for glider control. Okay, so what does the plan look like? This is a profiling plan here. This is showing the distance from the goal in the planning model. So this is how you thought it was going to be, and this is really how it turned out. Okay? So obviously, it never turns out as good as you thought. And then this is just looking at distance squared, because normally, you know, you like look at the measure. That's a more common error measure, right? So when we do this in simulation, this is what you get. What you do is you look at the Pareto optimal curve for various profiling points. So this is, as you increase the number of profiles, how far you get driven off of your target point. So this is what you plan. So if your model was perfect, you would get this. This is actually what you see is executed, and then this square boxes here is evenly spaced. So again, if your model is perfect, this is actually 6 days advanced prediction, and then this is the difference between planning and nature, and then this is your actual performance. So we actually outperform significantly, but at any one of these data points, it's not at the statistically significant level. So we're actually running more exhaustive tests, but really the proof in the pudding is in the real world. So this is actually from a deployment we did in April 2015 as a ground truthing experiment for what's called AirSWAT. AirSWAT is one of the next big, well, SWAT is one of the next big ocean missions by NASA. AirSWAT is an airborne version of that instrument, and so they fly that instrument around, they collect data, and they see how the instrument performs, and then all these different ocean assets are stuck into the ocean to compare what the instrument measured versus what they believe actually happened in the ocean. So what you see here is profiling, and this is particularly one of the quantities that they measure. I believe it's pressure. And out here, you can actually see, sorry, I don't know why this is black here, but this is when our dynamic controlling algorithm is controlling the profiling. And we actually were really unlucky here. So what happened is we started out with this long deployment. We were out in the ocean a few days. They said, OK, we're going to get a baseline. Then they said, we're going to turn your algorithms on. And then like a day and a half later, a storm front came in. And it's bad for two reasons. First of all, that's the case where the model sucks the most. Okay? And second of all, the storm was bad enough, they decided to recover the instruments. We were supposed to run an entire week, which would be like way out here in terms of data. So we have some interesting results here. This is actually showing the actual observed versus ROM's predicted model currents in each direction for one particular float. This is for float 6665. And you can see they're all over the place. And this is where it gets really interesting because we can measure the actual currents with this float. Second of all, if you look at the actual float performance, this is the start location. This is where ROM said the float was going to go, and this is where it went. This is where ROM said it was going to go, and this is where it went. So this is showing how the model has some problems. In fact, the model kept saying it's going to go north, but it just kept going west. This is the other float. So this is saying this one's even worse. So this one, ROM says it's going to go west, and it went east. Right? Here, ROM says it's going to go east. I'm sorry, ROM said it's going to go south and then west, and it went east. But the interesting thing is we actually measure the impact of the model accuracy on performance. Well, how do we do that? We actually take a variable number of prediction days in advance, and then we look at how badly that model correlates. So what this shows is this is the model RMS error for 0 days in advance. So your planning and nature are perfect, right? This is for 2 days in advance, 4 days in advance, 6 days in advance, 8 days in advance, and 10 days in advance. And so we have both batch and continuous planning. Batch is you plan out the entire deployment, and you do an open loop. Okay? So obviously, that's not going to incorporate any environmental feedback. continuous planning, what you do is you actually, every time you surface, you resynchronize your position. So what this tells us is these are baseline even profiling, and baseline staying at the bottom and then just coming up, the Argo profiling. These lines show the actual RMS error that we observe. So still here, we're getting a significant improvement in performance. Out here, at 0.24, we don't think so, and so on. So I'm just going to wrap up here. One of the reviewers actually made a very good comment. Well, it's ridiculous to use a zero-cost completion estimator. So we actually developed the completion, estimating what the cost is going to be for the remainder of your plan, and you get exactly what you'd expect. As you increase the weight on that estimation, your search nodes expanded goes down, but your quality of your plan decreases commensurately, right? So no surprise there. We also use this in predicting where the floats would go before we deployed them. And what would we really like to do with this? We have some concepts in the works to send these floats, and these are currents that you see underneath the ice shelf in Antarctica. And you want to ride these currents in and then ride these currents out, particularly with an EM apex because you can measure the currents. This area here has never been explored. This is the Ross ice shelf. This is the Rodney ice shelf, 970 kilometers deep. And this is all part of a program we have at JPL. The most interesting thing here is basically we want to develop vehicles to drop into Europa, melt through the 10-kilometer thick ice cap, and explore autonomously there. And it completely has to be autonomous because you'll get one ground contact about every 3.5 days. So what's the next thing we're doing? We actually have a deployment on the 28th of August for about a week where we'll be deploying a set of different assets. Come see my software demonstration today, or there's a paper in Spark on this. With that, I'm done, and thank you for your attention. Questions? I don't know if I...
Okay, I've got one.
Oh, great.
So, it's the case that they sometimes want to deploy a float.
There you go.
Is it the case that they sometimes want to deploy a float in a static location, so they want to keep it someplace, but the currents simply won't permit it? And in that case, what do? Do you repeatedly deploy them and just collect them later, or what?
Yeah, they generally, well, in this case is unusual. They actually collected them back. But the majority of the ocean, nobody ever goes to. So if we flip back to the Argo presentation, they're like all these floats in the Southern Ocean near Antarctica. Nobody ever goes there. So, for example, to this Antarctic thing that we want to do, the ship time alone is like over $1 million, and the floats are only say $20,000, so no one's ever going to pick them up. So one of the things they do in Argo is they have a number of ways of deploying them. They typically pay freighters to just throw them off the back of the ship. They have one that just goes out the back. The Navy can also drop them out of a C-130 that's flying at like 500 feet. I have pictures of that if people are interested. These are very rugged floats. So generally, you do not recover them. That's why you have to rely on the sat phone to get the data back. Yeah. And like for the Europa case, you actually have to go out and come back with an acoustic modem back to your base station to transmit the data.
I was just curious if there's any potential model here of even cheaper, crappier disposable floats that indicate local currents or sort of most up-to-date currents and sort of report that information to the more expensive science gathering floats and having some sort of coordinated network, or if that's, just the cost of getting a float as high sunk cost no matter what. There's no...
No, you're right. So the floaters that I mentioned might be as cheap as $100 a piece, and those just sit on the surface and they gather all of the same, similar data. So what's called CTD, conductivity, temperature, and density. Well, I guess they wouldn't conduct density because they're already at the surface. So that's like the simplest sensing. I'm not exactly sure how they get their data back. I suspect they must get it back via sat phone because how else would they? They're definitely not going to recover those. In most of the applications, these vertically profiling floats are not recovered.
And can you talk to them at all, or is it receive data only, or can you?
No, you can go both ways. It's a full sat phone. In fact, the sat phone also provides a secondary fix. There's both a GPS and somehow the sat phone is also providing location data, because in the telemetry we see both, but the GPS is usually better. Yeah. Okay. Yeah.
I just had a really quick question. So the ice shelf was fairly interesting.
Mm-hmm.
Like, how far can you store with remote control devices?
Not very far, like a few kilometers at best. So ROVs they've sent down. There was a project to actually drill through the ice shelf in the 70s, but it's like millions of dollars to drill through the ice shelf. And I think they only drilled through in like 2 places. And it was like very controversial, where do you drill? So like all the Antarctic scientists are like literally arguing over it for months. Yeah, that's actually one of the biggest challenges to the Europa Sub-Ocean Explorer mission is how do you get through ice that's 10 kilometers or more thick. In fact, the current estimate is it would take a year to burn through.
Thank you very much.
Okay, thank you.
This was yours, right?
Our final speaker in this section is Supriya Ghosh, teaching planners for setting up base stations in Virgin Meadows.
Okay, thank you, David. This is a joint work with Pradeep Bharakantam from Singapore Management University, and I am going to talk about the strategic planning in emergency medical systems. Emergency medical systems is an important component of public healthcare services. The basic cycle in EMS goes through these 5 stages. Once a request comes into the system, the operator dispatches the nearest ambulance for the request. The ambulance goes to the incident location, provides some initial treatment, and then it transfers the patient to the nearest hospital. And after that, the ambulance returns back to the same base where it has started. The driving factor in EMS is the response time. That means the time between a request coming to the system and the ambulance goes to the incident location. And reducing that response time by even a few seconds can save human life and can have a great value. So, as the location of the bases and the ambulances do not change in the EMS for a long time, the strategic planning can have a major impact in reducing this response time. So let me start with a simple example. So here we have 3 possible base choices. We have 2 requests and we have a budget for 2 ambulances and 2 bases. Now, if we place base 1 and 2, then we'll have the following scenario. So as the request 1 came into the system first, it has to be served from the nearest base 1, and then request 2 has to be served from base 2. So the response time will be 10 minutes and 30 minutes. On the other hand, if we place base 1 and 3, then you can see that both the requests can be served within 5 minutes. And moreover, we can reduce the response time by 30 minutes even for this kind of simple example. But the strategic planning in EMS is really hard because of the following reason. First of all, the demand in EMS is dynamic and it changes over time. But even with the static demand scenarios, this is a computationally challenging problem because the possible base numbers can itself be large, and for an efficient planning we need to consider all the possible combination of those possible bases, and our action space will be exponentially large. The next problem is that to compute the utility of a given base set, we need to optimally allocate the ambulances to those bases. And so there is a direct dependence between the ambulance allocation problem and the base placement problem. The next problem is that the budget for resources, that is how many bases and ambulances we can deploy in the system, it is dynamic and it comes over time in different chunks. So our solution has to adapt all those scenarios and it has to be incremental in nature such that we can apply our solution in the existing system as well. And lastly, this problem is an extension of the K-center facility location problem, which is a well-known NP-hard problem. So this our goal is to find the efficient location of the bases and to allocate ambulances on those given bases such that we can optimize this widely adopted metrics in EMS. The first one is the bounded time response. That means we want to maximize the number of requests that can be served within a given threshold time. And the second one is the risk-based objective, where we want to minimize the response time for a certain percentage of requests. The existing research in EMS is mainly in the direction of operational planning. That means they want to allocate the ambulances into a given set of bases such that most of the requests can be served efficiently. But in this kind of research, they assume that the base set is already known to us. But as I have shown in the example, this kind of base choices can have a major impact in the system performance. So we actually go one step back and we find the optimal location of the bases along with the allocation of ambulances to those bases. The other thread of research is the strategic planning in large-scale disaster responses. But these solutions are not applicable to EMS because the demand in EMS changes over time every day. So to bridge that gap, here is our following contribution. We first provide a data-driven greedy algorithm where we add the bases incrementally in each iteration, which has the highest marginal gain. But the greedy algorithm cannot solve the real-world large-scale problem, so we take an accelerated version of the greedy called lazy greedy algorithm to optimize both the widely used metrics. And finally, we evaluate our solution on a simulation model which is built on the real-world dataset. So here is the brief overview of our solution approach. Here, the given input to us is the possible base locations and a fleet of ambulances and a request log for a certain period of time. And we initialize the resulting base set as a null set. Now in each iteration we compute the marginal gain for each of the bases by optimally allocating the ambulances to those resulting base sets. So we solved this problem by using an optimization formulation. And once we compute all the marginal gains, then we took the base which has the highest marginal gain and we add it to the resulting base set and remove it from the remaining base set. So let me start with the ambulance allocation problem. The ambulance allocation problem can be defined with the following tuple. We have a set of request log where each request is tagged with the following tuple. The T is the time when the request came into the system, S is the origin location, and H is the destination hospital. B is the set of base locations, A is the fleet of ambulances, T is a 2D matrix that shows the travel time between any two base locations, and finally L is the utility function. So for example, in case of bounded time response, we can set the utility function such that if the request is served within 15 minutes, then we will get a reward of 1, otherwise we will get nothing. So with those inputs, our goal is to our goal is to find the allocation of ambulances to each of the bases such that we can maximize the number of requests that are served within a threshold time. To do that, we have employed the following decision variables. Here X, R, L is a binary decision variable which is set to 1 if request R is served from the base L. So the objective of our MILP is to maximize the number of requests that are served within 15 minutes. First set of constraints says that a request can only be served from only one of the bases. The next set of constraints says that a request can only be served from a base if there is an available ambulance to that base. And finally, the last set of constraints says that the total number of allocated ambulances and the total number of available ambulances has to be equal. Now, if we solve this MILP using any kind of black box solver like Cplex, then we can find the utility of those given base set along with the allocation of ambulances. We can use a similar MILP model to optimize the risk-based objective, but in that case we need a set of additional constraints that will ensure that at least a certain percentage of requests has to be served within a threshold time bound, say delta, and in the objective we want to minimize that delta value. So one of the reasons for choosing the greedy algorithm is that one of our objective function is submodular, and even the greedy algorithm provides some sort of quality guarantee. a function which is defined over a set of elements is submodular if the marginal gain for adding an element to the subset is always higher than adding the same element to its superset. Now we show that the bounded time response objective is submodular in nature, and even the greedy algorithm provides at least 63% of the optimal solution. So the proof is simple, because the bounded response time objective is nothing but the set of requests that can be served from at least one of the base of the given base set. So we can exploit the simple properties of set theory. So here in the first figure, the red portion shows the marginal gain for adding a base into the subset, and in the second figure, this red portion shows the marginal gain for adding the same base into its superset. So the green portion is nothing but its difference, and it will always be greater than 0. And this proves that our objective function is submodular. But the greedy algorithm scales very poorly when you increase the number of bases. So we took an accelerated version of the greedy called lazy greedy approach. So in the lazy greedy approach, the first iteration is exactly same as the greedy. So we compute the marginal gain for each of the bases, and we keep track of all those utilities, and we say that these utilities are the upper bound for the next iteration. And then we take the best base and add it to the resulting base. But from the next iteration, we choose the base which has the highest upper bound, and we compute the marginal gain for adding that base to the existing base set. And if after updating that value, if that marginal gain is still higher than all the other, is still higher than the upper bound of all the other bases, then we already find the best base without exploiting all the other bases. And then we can add that base to the resulting base. And otherwise we'll continue that process with the other elements. Now this process will continue until our budget constraint is violated, or the marginal gain is not significant enough. So one of the good thing about the lazy greedy is that it provides, we can compute an upper bound for the lazy greedy approach. So this proposition says that at any point of time, we can compute the upper bound for the optimal solution, which is nothing but the utility of the resulting base set plus the cumulative upper bound of all the remaining base sets. So this way we can find at any time how far we are from the optimal solution. So that's all from the technical part. For the experiment, we have done our experiment on a real world data set from a large Asian city, which has 58 bases and 58 ambulances, and we have the request log for 1,500 weeks of request log, which is generated using Poisson distribution based on the real world demand for last 2 months of demand. And we divide that request logs into 3 sets. First we generate 10 policies based on the 10 weeks of request, and then we validate the best policy on another 500 weeks of request logs, and we took the best policy, and then we test that performance of that best policy on the remaining other weeks of request logs. For the comparison, we have taken 3 benchmark approaches. The first one is the baseline approach, where 1 ambulance is allocated to each of the bases. The second one is a recent paper where they want to allocate the ambulances in the given base set such that the bounded time response objective is optimized. And the third one is a 2015 AAA paper where they are optimizing the risk-based objective. And finally, we compute the utility of all those approaches by using an existing event-driven simulator. So this simulator works as follows. First, we initialize the event list, which is nothing but the set of requests which are sorted based on their arrival order, and then in each iteration we pop 1 event, and this continues until the list got empty. If that pop event is a request, then we dispatch the nearest ambulance for that request, and we also add an job completion event to that event list. And if the pop event is a job completion event, then we free the ambulance such that it can be utilized for the next request. So we have 3 sets of experimental results. in the first set of experimental results, we show the runtime comparison between the greedy and the lazy greedy approach. So in this figure, in the x-axis we vary the number of requests, and in the y-axis we show the runtime in the logarithmic scale. We can see that the greedy approach cannot solve the problem with more than 1000 requests within the cutoff time of 1 hour, while the lazy greedy approach can easily solve a problem with 1500 requests within 2 minutes. So it gives a huge computational gain. Similarly, in these figures we vary the number of iteration in the x-axis, where in each iteration we are adding one base, and in the y-axis we show the runtime in the logarithmic scale. And both the figure has the consistent pattern, so the performance of the lazy greedy is much better than the greedy approach. The next set of results, we show the performance of the ambulance fleet size. So here in the x-axis we vary the number of ambulances, in the y-axis we show the number of bases required to accommodate those ambulances, and in the z-axis we show the number of requests that are served within 15 minutes. So you can see that as we increase the number of ambulances, the performance of the system increases monotonically. Similarly, in case of risk-based objective, if we increase the number of ambulances, then the alpha response time reduces monotonically, so the performance actually improves monotonically. And in both the cases, if we increase the number of ambulances, then we need additional set of bases to accommodate those ambulances. Finally, the last and most important trade-off result is the performance of our approach in comparison to other benchmark approaches for the testing data sets. So here in the x-axis, we show the percentage of requests that are served within 15 minutes. The red bar is our approach for the lazy greedy, and in that case we continue the process until the marginal gain becomes 0, and we get a set of bases with 49 base. And then the orange bar is also our approach, our lazy greedy approach, where we stop the process once the marginal gain becomes less than 2, and we resulted with 43 bases. So as you can see that for all the cases, our approach significantly outperforms all the other benchmark approaches, and in all the cases we can serve at least 3% extra requests within 15 minutes by utilizing significantly less number of bases. In case of risk-based objective, the interesting point to note here that our approach converges with only 39 bases, where all the other approaches are utilizing 58 bases. So by utilizing less than 75% of the bases, our approach is either highly competitive with the other benchmarks and significantly outperforms the baseline approach. So to conclude, strategic planning in EMS is a computationally challenging but practically important problem. We employ a lazy greedy approach that add the bases incrementally in each iteration, and it is able to solve the real world problems. And finally, we experimentally show that our approach significantly improves the performance of the system over the existing benchmark approach on real world data sets. That's all. Thank you.
I'm just wondering, did you try adding the base allocation in your mathematical model as well?
No, because then we cannot solve the problem using like those black box solvers, because in that case we need to combine both the allocation, ambulance allocation as well as the base placement problem. So suppose if we have like 300 possible base choices, then we'll have to create a binary decision variable for each of the bases, and like all those things will be combined with the ambulance allocation problem as well. So it will become very complex, I guess.
So facility location is like fairly popular model and it has very strong relaxation. So I'm just wondering if you could do that and compare perhaps the results of your greedy base assignment algorithm to a model that completely models the problem.
Yes, I mean we can do that, but one of the problem with that is I mean, for the real world problems, our solution has to be incremental. I mean, in some cases, we even don't know that how many exact bases we can deploy beforehand. You know, so, I mean, if we don't have all those exact details, then we cannot develop a concrete mixed integer program where, like, you can say, okay, this is the threshold value, and we can just plot this many this many bases. So, but yeah, we can try it in the future, and we can.
And a second question. So, with your with the way you use your greedy approach to add bases, did you investigate at some point in your heuristic taking a base away, and that might actually improve your objective function at that point?
Can you please repeat the question?
So you add bases in a greedy fashion, right? But at some point it might actually be advantageous to remove a base from the set that you have. I'm just curious to know if you looked at that.
No, we actually haven't looked in that way. But I don't think, because of this property of the lazy greedy, and as I have shown that one of the objective function is monotone submodular. So actually, like, this kind of situation will never happen. I mean, this is a monotone submodular, so the objective always, like, increases. It never, like, if we just remove one base and replace with other base, it cannot, like, improve the objective. Yeah.
It's maybe just a follow-up to the one. Just imagining when you remove a base and then just, remove an ambulance, you can put it to another position. That might improve the performance, right? So it might be advantageous to do some kind of local search. If you get a new ambulance, then just try to shift the other ambulances a little bit to get more performance out of that.
So there is, like, two level of decision making here. So one is the adding bases, and another is the allocating ambulances, right? So yeah, so in case of ambulance, we are solving this problem optimally, how to allocate the ambulances optimally. So the solution of the ambulance allocation is already optimal to us, because we solve it using mixed integer program. So this solution is already optimal. So I mean, if we just reshuffle them, I don't think the result is good.
Yeah, so this